Okay. Hello? Okay, let's start. So, couple of logistic questions. You should be working on your homework assignment, your first homework assignment. The second homework assignment is going to be out. It's going to be out next week. If you have any specific questions about homework 1, talk to TAs. There are office hours and such that are posted on Piazza. And that's the best sort of way for you to, figure out what you should be doing for homework 1, okay? So talk to TAs. Pretty much every week, 3 TAs are holding office hours. So, if you have any problems, talk to TAs. You should be well underway with your homework 1. As I mentioned, the second homework is going to be out next week. Let's see. Also, this Friday, I believe, it's going to be confirmed on Piazza. We're going to have recitation for the second homework. Basically, how to use the resources, the supercomputing resources that you will need to use for your second homework. Okay? So we'll post on Piazza. It's most likely it's going to be this Friday at 1:30 p.m., same location. Okay? Because for the second homework, you're actually going to be implementing Q networks, deep Q networks, and things like that. And we're going to cover those in our next class. You should also be thinking about your projects. I believe on March 19th, you're going to have midway project proposals that are going to be due. We're expecting it to be 3 pages. TAs will post on Piazza what is expected from you for the projects. The expectation is that you're going to have at least 3 sections on for your project proposal. It's going to be introduction, motivation, what is it that you're trying to do. There's a method section where you will describe what method you're trying to do, what is it that you're trying to do. Is there a method? Is there an algorithm? What the problem you're trying to solve, and plus some preliminary experimental results. So the expectation is by March 19th, you should be able to provide some preliminary results. Of course, these are not full-blown results, but you should basically describe what data set you're using, what simulation environment you're using, and some initial results. Okay? Expectation. The reason why I want you to have some preliminary results is because in many cases, if you don't do that, a number of students would choose ambitious projects. I'm going to do X, Y, Z, which is all great, up until you actually start implementing it and looking at your results, at which point you realize, whoa, I'm completely off what I was trying to do, right? So the goal would be for you to run some initial results, right? Because you don't want to be switching your projects 2 weeks before the final projects are due, right? You don't want to be in a situation where 2 weeks before the projects are due, you're basically saying, whoa, I'm completely way off what I was trying to do, okay? Any questions? How's homework 1 going? Pretty easy, huh? Okay, so today we're gonna, for this week, what I'd like to do is I'd like to cover convolutional neural networks. In particular, just give you an idea of what they are and how we compute those. Because I believe in the second homework, we're going to have at least 1 question on using convolutional networks, but I believe it's going to be a bonus question. For your final projects, most of you will most likely use some form of a convolutional neural network if you're going to be working with simulators or with vision-like data. And next class, we're going to look at a combination of Q networks with deep learning, and we're going to look at the deep Q networks and at different extensions of these models. Okay, so we'll get some ideas of how we can combine function approximations with reinforcement learning. Okay, so let's continue looking at. This is going to be a little bit of a detour, looking at computer vision. Okay, so we'd like to design algorithms that can process visual data. To to accomplish a particular given task, for example, a classification task. Okay? Now, as I mentioned in the last class, when you apply these models to reinforcement learning, typically the output is not going to be a sunflower, but the output would be a set of actions, right? What action you need to perform. So think of it that way. But for example, in computer vision, in object recognition task, given an input image, you have to identify which class it belongs to. Okay? And deep convolutional networks, they sort of have multiple operations. The most important operation is the convolution, something that we'll cover today. And then there are a few other operations that people use. There is something that's called pooling. Sometimes people use pooling, sometimes people don't. There are different ways of doing pooling. There is also something that's called normalization. Sometimes you use normalization, sometimes you don't. We'll look at those as well. And typically you go through some densely connected layer to get your output. Even though the most recent models actually just keep the convolutions all the way to the very top. And so convolutional networks leverage some of the ideas. And there are multiple ideas that you can leverage. So the first one is local connectivity. That's important. Which is actually what's making convolutional networks work remarkably well. Parameter sharing is another idea that we're going to be using. And convolution, obviously. And then things like pooling and subsampling of the hidden units. And we'll see some examples of that. Okay? So let's look at the first idea, which is a local connectivity idea. So imagine that I give you an input. This is an RGB input. And let's say you have 3 channels. If you have 1 channel, if it's a grayscale image, and you have 3 channels if it's a RGB image. So what the local connectivity does is it basically says this unit here, this hidden unit, is connected to only some local patch in all 3 channels. So it's connected to this patch only. Okay? So that's what it means being locally connected, right? So the input to this particular hidden unit is just looking at this area of the image, right? And you can imagine that, this is another example. Another unit is just looking at these inputs, right? So you're basically restricting your connectivity. And obviously that helps in terms of reducing the number of parameters, right? So if you have an image which is 200 by 200, you basically, if you have, let's say, 40,000 hidden units, which is a lot but not that many, for some high resolution image, then you're going to have about 2 billion parameters, right? So that's way too many parameters, which is impossible to feed. But at the same time, we can use some prior knowledge about images. We know that the spatial correlation is local, right? Things that tend to happen in this part of the image might not necessarily be highly correlated with what's happening in this part of the image, right? So, but there is a strong local spatial correlation. And if we have too many parameters, we'll require a lot of training data. Okay? So that's a constraint. So that's something that we can do. On the other hand, let's say if you have a filter size of 10 by 10, so we only, like this particular hidden unit, is only looking at the 10 by 10 patch. Right? So if we have 40,000 hidden units with a filter size of 10 by 10, then we only end up having 4 million parameters, right? As opposed to 2 billion. So obviously there's a dramatic reduction in the parameters that we can use if we're going to be using local connectivity. So this is sort of a trivial idea, but a very powerful one. So this particular parameterization is good when the input is registered, right? What that means is that, let's say you're trying to recognize faces, and your faces are always located at that particular part of the image, right? So for example, these kinds of models are highly used whenever you're looking at things like fMRI images. When you get the brain scan, you're looking at certain configuration where the images are very registered, right? You know exactly where things are. And you're just looking for particular patterns. But In many cases, what we're going to be doing, particularly when we're working with natural images, is we're going to be using the idea of parameter sharing, which is also a fairly straightforward idea. But what we're going to do is we're going to share the matrix of parameters across some units or many units. And sometimes units are going to be organized in something that's called feature maps. And these feature maps are going to be sharing parameters. And hidden units within the feature map cover different positions in the image. So let me show you an example of that. Let's say this is the feature map 1. So here you have connections. So this hidden unit is connected to this part. This hidden unit is connected to this patch. This hidden unit is connected to this patch. But all of these parameters, all of these blue parameters are the same. Okay? We'll look at the second one, the second feature map. It's also connected to all of these patches, but these parameters are the same, right? So why do we do parameter sharing? So each feature map will detect certain features. Let's say this feature map might be detecting vertical edges. This feature map might be detecting horizontal edges. This feature map might be detecting, 45-degree edges, right? You can think of it that way. And the idea of why we do parameter sharing is the expectation is that, the vertical edge is likely to be here, here, or anywhere in the image, right? So that's why we're kind of looking for features, specific features in any part of the image, right? And that's a natural assumption because in natural images, if you take the sunflower, you move it over here, then, you still want to be able to detect features, right? Or in the entire image. So same color means the same matrix of connection, and Wij here would be the matrix connecting the ith input channel to the jth feature map, right? So think of it as Wij's. And so you're going to be sharing matrix of parameters across certain units. We can also think of it as a convolution operation with certain kernels. Okay? Because think of it as a convolution, you extract the features at this location, this location, this location, this location, and such, right? Throughout the entire image. Right? And this forms the basis of convolution. Right? So it's the idea of local connectivity, parameter sharing, and we're scanning for these features in the entire image. Okay, these kinds of ideas, the convolution existed for a long time, but one of the things that makes it interesting, and we'll see, is that obviously within the deep learning we're actually going to be learning what these parameters should be. So it's almost like learning what the kernel function should be that we're convolving with an image. Okay, so now let's look at the convolution, how convolution is done. How many of you have done convolutional neural networks? A few. So you're probably familiar with how it actually operates, but let's look at it in a little bit more detail. So think of it as follows. Each feature map forms a 2D grid of features, right? So we take a convolution here, we look at a particular patch, think of it as a 5x5 patch, 5x5 convolution. We scan it throughout the entire image, and we just record the responses, right? So the activations, think of it as an activations of the hidden units here. If we have multiple feature maps, we're going to be doing, applying this convolution at different, with different kernels here. And we can have all of these different feature maps. So what is a convolution? So it can be computed with a discrete convolution of a kernel matrix, Kij, which is the hidden weights of the matrix Wij's with the row and columns flipped. So there is a proper definition of the convolution, but think of convolution matrix, Kij, as the matrix Wij that we're trying to learn. It's just a flipped matrix. So for example, here, an example of creating one of those feature maps. You have your kernel, Kij, which we're going to learn. You're convolving it with an input xi, right? So xi is the ith channel of the input. Kij is the convolutional kernel. Gi could be a learned scaling factor, or it could be 1. And G here is the hidden layer. Oh, sorry. It should be like 10H is the hidden layer in this particular example. But it doesn't have to be 10H. It could be ReLU, it could be sigmoid, whatever nonlinearity you're using. And you can also add bias, right? So it's a very simple idea when you think about convolutional models, right? You're just creating these feature maps by convolving a 5 by 5 or 10 by 10 or 3 by 3 convolution across the entire image. You're creating these feature maps. Obviously, it's a very repetitive operation, the convolution, and there are packages that can basically do it extremely efficiently for you. So here's an example of applying a convolution, right? You can think of it as a vertical edge, right? This particular convolution is what it looks like, black, 0, and white. So it really is looking for the contrast. So if you take this 3 by 3 convolution and apply it into the entire image, that's going to be the output. That's what the feature map would look like, right? So it's almost like finding the vertical edges, right? And you'll be surprised that, for example, if for those of you who've seen things like applying reinforcement learning for examples like Atari games, you know, there's like a ping pong game. And so finding where the, what do you call it? You know, when you play ping pong, you have these kind of like vertical bars that are moving around. Or whenever you play breakout, you have a vertical bar that moves around, right? Being able to detect where the vertical bar is or horizontal bar is quite important. And these kinds of features can do it fairly precisely, right? So that's what the convolution looks like. Now, here's another example. Imagine you have a 200 by 200 image, right? Which is a reasonable size image. You use 100 filters with a filter size of 10 by 10. So these are 10 by 10 pixels, right? The filter size of 10 by 10. Basically, you end up with only 10,000 parameters, right? And this is having 100 feature maps. Typically, the number of feature maps in layer 1 is just maybe, you know, on the order of like 16, 8, 16, 32. So you can also see a drastic reduction in the parameters. So it's interesting, in convolutional neural networks, the number of parameters is actually, the number of learnable parameters is actually quite small. It's the computation that's expensive, right? Because you have this high resolution image and you have to convolve it with 100 different filters, right? And obviously you can also parallelize it. You can do it across multiple feature maps or across multiple channels in parallel. So there's a lot of speed ups you can do here. Okay? So that's important to know. That convolutional neural networks, they kind of these interesting models where you use spatial locality, you use parameter sharing, and that really, you know, shrinks the number of learnable parameters. Yes, question?
Would you ever want to learn the elements of Kij?
Yes, we're going to be learning the elements of Kij. The idea here is that Kij is really Wij, or Wji in our case. So we're going to be actually learning the kernels, right? Yes?
When you say 100 filters, is that 100 feature map?
Yes.
Okay.
Think of it as 100 feature maps, that's right. Or sometimes people call 100 filters because each filter, let's say it's 10 by 10 filter, right? So once you convolve it, that defines a feature map, at least at the first layer. It's basically telling you what the response is. Like, for example, here, this would be one feature map, and this would be a filter of size 3 by 3, right? We're going to be learning throughout the process. The beauty of convolutional neural networks is actually you're learning what these things are as to optimize for your recognition accuracy or detection accuracy, or whatever is it you're optimizing it for. So we're going to be learning what these kernels are. Yes?
Are those just randomly generated, those kernels?
This one?
You have 100 filters. Are these kernels randomly generated resultant on the image?
Yeah, so the way you can think about it is that initially, these filters, these kernels are randomly generated, but through the process of learning, we're going to learn what these filters are, right? You're going to be using backpropagation, because if you think about this model, you can just think of it as a standard neural network with a very specific architecture. So the backpropagation algorithm, everything still works. You're just designing a specific architecture for images, right? So you're putting these inductive biases. So let's look at the pooling and subsampling. That's another operation that's typically common, right? Now, there are different ways of doing pooling. In most recent networks, you actually don't need that much of a pooling, or you actually don't do pooling. You can kind of like learn what the pooling should be. But the idea is the following. Pooling is performed in a non-overlapping neighborhoods of, known as subsampling. So what you do is you basically say, this is your feature map. Look at, a 5 by 5 neighborhood, or maybe a 4 by 4 neighborhood, and perform some kind of a pooling operation. For example, max pooling is very, commonly used technique. So what you do is you look at, a 4 by 4 neighborhood, and you pick the maximum element here, right? And that's what subsampling does, and that's what pooling does. So now you reduce the resolution of your feature maps, right? Pooling has one interesting property, which is what it does is it makes sure that your representation down the stream is invariant to local transformations, right? Imagine my face. You're detecting my eye here, while you're detecting some vertical bar here. If I move my face 2 pixels to the right, or 1 pixel to the right, then by performing this operation here, your feature is not detected here, it's detected here. Because you're taking the maximum, you're just still responding that there is a face here. You're losing precise location of the face, right, up to a few pixels. But it actually makes sure that small translations in the input doesn't really affect your representation, the high-level representation. And that's an inductive bias that a lot of these models have. Yes? If you sort of want to reconstruct back the original face, let's say, and you want to be very precise where the features are, then it becomes difficult. You have to remember where things were. And when you're doing pooling, you typically can't. You're losing this information. You're specifically saying, I'm going to be losing precise location of my eyes, or precise location of my particular feature, but at the same time, I'm going to be gaining this translation invariance property. So here, xi is the ith channel, for example. Xijk is the value of ith feature map at position jk, and so forth, right? And p and q are the the neighborhood of what you want to pool over. And then you get a pooled or subsampled layer. And pooling typically helps. In many cases, you can also design, instead of doing the max pooling, you can actually build a network that kind of looks at the neighborhood and just looks at the response. You kind of sometimes, you can actually learn what these things are. Right now, you're just doing a max pooling operation, but you don't have to. Right? Think of it as another kind of convolution, but at the same time, these are non-overlapping, right? So you're kind of figuring out what the most important information you should pull from that location. So here's an example of doing pooling, right? Let's see. So if I just do max pooling here, then I'm just going to be recording 0.19 here, 0.19 there, and such, and 0.75 here, right? So what this means is that, look, if I actually move this thing to the right by 1 pixel, my response is still going to be 0.19, right? So that's kind of like a saying that the value of the feature, the response, doesn't change due to small local transformation. And in fact, it is the case that in many of the convolutional networks, if you take an input and you slightly shift it to the right, the overall output is not going to change. And you want that because that's the property of natural images, right? You take an image, you translate whatever the object slightly to the right, to the left, to the right. You don't really lose the identity of the object. So it introduces invariance to local transformations, and it reduces the number of hidden units in each layer, right? So that's another operation that's typically is happening, is because imagine that you have some high resolution image. You create 10 feature maps. Now you basically have 10 of these images. So you have you have an explosion in the number of compute that you need to do. By doing pooling, you're basically reducing the size of those feature maps, and then you go to the next layer. And then there's a whole bunch of things you can do. Let's say you want to do segmentation. You want to accurately predict which pixel belongs to which class. You can add skip connections, so you can kind of construct a whole bunch of a lot of different architectures. So sometimes people use something that's called convolution and then deconvolution, going back through the bottleneck and extracting it back. You add skip connections and such to make sure you preserve some local connectivity. So there's a whole bunch of different architectures you can design here. And so this is an example of a pooling where you can make the detection be robust to the exact location of the eye, right? Because if you pool over these units, you take the maximum, then it doesn't really matter where the eyes are. If you move a little to the left, a little to the right, the output is still going to be the same, right? So this is by pooling, you're basically saying that the filter responses at different locations are robust to the exact spatial location of the features that you're looking at. And that's a very good inductive bias to put into these models. It works in practice, it works extremely well. So if you look at the overall convolutional networks, like these are pretty old models. They've been around since late 80s, right? And the idea is that you have some input. Here you do 9x9 convolutions. You have a bunch of filter maps. You do pooling. You pool them. You do again 9x9 convolutions. You have a whole bunch of them again. And then maybe you pass them through the fully connected layer, and then you do the classification or regression or whatever it is that you're trying to do. Okay? So these are kind of like, overall structure, overall architecture. In the last few years, I'm going to show you some examples. The precise combination of these things is changing, right, depending on the application. So we're going to look at some examples. But roughly speaking, that's what these models are doing, right? You convolve, you detect some features, you pool, you convolve, detect more features, you pool, and so forth. Notice that this entire model is differentiable. So you have some objective function, like a classification, you look at cross-entropy or whatever your objective function is. You can differentiate the loss with respect to all the parameters in this model. So effectively, you're learning what these kernels should be, right? So it's very much data-driven approach. It's interesting because these models been around for a long time, but they never worked well. And the reason why they never worked well is because we didn't have enough data to train these models, to train them reliably. And also we didn't have enough compute to train them reliably. So a lot of work in the vision was done in terms of figuring out what features we should be using here, right? People have used hogs and SIFT, Gabor-like filters, and sort of everyone was trying to figure out what's the right representation to use at the first layer, right? Because pixel is a terrible representation. Just pixels themselves is just very busy, not a very good representation to learn from. Up until these networks really showed up and basically said, no, you're learning everything from pixels. Because anytime you design your own features, you lose some information. Unless you know something about domain, specifically about domain that you're working with. And you have very good prior knowledge. So these models are right now pretty much dominating the computer vision field because they work way better than anything else that people could have come up before. And this is, again, so think of it as like, this is your feature, you're convolving it, right? And you're getting the feature map. And then you're pulling it to get some representation, right? And then you get another feature map, you're convolving it. And then you get another feature map, you're convolving it, and such. And that's the operation that gets passed forward. And obviously there are software packages like, if you're working with PyTorch or TensorFlow or Keras, they all sort of designed to make sure that you can run these computations very efficiently on GPUs and you can compute the gradients, right? You can imagine that computing the gradients by hand here is a little bit of a tedious task because you have parameter sharing, so you have to take the gradient with respect to each one of those locations and average and so forth, right? But at the same time, if you think about this, this is just a standard neural network with very specific architecture design, right? So the entire learning procedure of backpropagation, everything is the same, right? It's just a chain rule for training these models. So for classification, the output layer could be, for example, a fully connected layer with softmax nonlinearity. So here the output again would provide the conditional probability of each class, right? You compute what's the probability of a particular class. The network can be trained by stochastic gradient descent. Backpropagation is used as the same way as you would have used it in a fully connected model. So it's exactly the same algorithm. You're passing the gradients through element-wise activation function. You can pass it through pooling operation, like a max operation, or the average pooling, or max pooling. And we're also passing it through element-wise activation function. Okay? So there are a few details of how exactly this is done, but this is very standard, very trivial. Okay? So if you are courageous enough, you could try, creating like a one-layer or two-layer convolutional neural network and, code or program the backpropagation algorithm and see if you can do it. Math-wise, it's pretty simple, but, I think that everyone should try just implementing convolutional neural network once so you know how it functions and how it works. Because in many cases right now, if you're just using the software without actually knowing how the whole thing works, it becomes a little bit funny. Because then you have no idea how it's done, so you have no idea how to fix things when things go wrong. Okay, so let me show you some examples. These are just some examples in the papers on, you can do optical character recognition. You can do house numbers, traffic signs, right? There's a bunch of papers you could look at. You could also do things like pedestrian detection, which is pretty remarkable. And look at these examples, right? And it's pretty difficult to do it. And it's kind of interesting because these images, I believe, are coming from something that's called Pascal dataset. So in the vision community, there were these datasets on the order of like 20,000 that have been set up as benchmarks for people to, compare the algorithms. And before, the convolutional networks came to life, basically, a lot of people were using other approaches like, creating features, running SVMs, and the whole setting was just a complete mess. You create these big vectors, you run k-means, you plug them into SVMs, and it was pretty hard. And neural networks never really worked in that particular domain because with 20,000 images, that wasn't enough to train the model, right? You can think of it that way. If you don't have enough data, the only thing you could do is you could start putting your priors, right? So you design your own features, you design your own pieces to make sure that you have a working algorithm. And that's what was happening with these data sets. And then ImageNet came online with 1.2 million examples, at which point these convolutional networks work remarkably well. So it's interesting. One of the person who won the ImageNet competition in 2012 was Alex Krzyzewski, and he is, I believe he's at Google now, but he basically built these convolutions on GPUs and such, and really showed huge gap in performance. compared to a lot of traditional algorithms. And it's kind of funny, they had this workshop on the competition, and this Alex Krzyzewski, he's a young PhD student, showed up at the conference and said, yeah, I just trained these models in my bedroom with a couple of GPUs, and these are results. And you have like these big computer vision groups that are like way behind, right? So, and Alex Krzyzewski is not a vision guy, he's not a computer vision person, which was even funnier, I thought. But from that point on, it basically changed the field of computer vision, right? And then people discovered that if you actually take features out of ImageNet, you take these models, you take these representations, and then fine-tune them on Pascal datasets, they work surprisingly well, right? So a lot of low-level features like finding edges, combination of edges, textures that you're getting from ImageNet are suitable for modeling a lot of different other tasks. So here's another example of object detection, right? Which is kind of cool. So this was an ImageNet data set. So you have, in this case, you have 1.2 million images of 100 classes, and this is just an example of a hammer. So look at this thing here. I mean, right? So it's a hammer. So you can see it's very noisy. But the nice thing about the data set is that you have 1,000 classes. So you have a whole different, there is like 50 different kinds of mushrooms in this data set, and then 20 different kinds of dogs. And this was in 2012, this was the model, a convolutional network that basically was the first one to kind of show really, really amazing results. And it caught a lot of people by surprise, including people who were working on these models, because nobody expected them to work so well. Here are some examples of on the top row, you see some examples, some accurate, some correct predictions, like container ship and such. These are some examples that are considered to be incorrect, right? So, the model says it's convertible, but the correct answer is grill. This is an interesting example. The correct class is cherry. The model says it's Dalmatian, right? So obviously, or like here, the correct class is Madagascar cat, and the model says it's squirrel monkey, right? So there is a lot of noise in the data set, but at the same time, by now, people have developed models that can pretty much outperform human, basically be on par with human performance. So this data set is more or less now solved with new architectures and such. The features that you're getting out, these features at the top level, are actually very useful features to use in a lot of different other tasks. There was a paper, something crazy, where they took ImageNet features and applied it to like medical imaging, like diagnosing, I think, breast cancer or something like that. And it worked reasonably well, right? Which should be even double surprising to you. You train a model to recognize mushrooms and dogs and hammers, and then you apply it to medical imaging, and they work pretty well, right? Which tells you something about the notion of features that you're learning here, right? In today's world, there are a bunch of different models. There is OxfordNet, VGGNet, there is GoogleNet, there is ResNet. There are models that are pre-trained. And what happens is that people just take the features and apply them to your own task, your own vision task. So let me spend a few words about the architecture. How can we select the right architecture? In fact, as I'm pointing out here, in the last 20 years, we've been trying to figure out how to tune features, right? What's the right features? Now we're basically tuning architectures, right? So you go from tuning features to tuning architectures, which I think is a step forward, but it's still kind of interesting. And so you're doing manual tuning of architectures, depth, width, parameter count, and you typically have a number of hyperparameters. Number of layers, number of feature maps, and the number of hyperparameters can be quite large. So you need to do cross-validation If you want to do grid search, searching over the number of parameters, hyperparameters, like what learning rate you should be using, how many layers, are there a certain regularization, what's the dropout, and such. There are smarter strategies like random search or Bayesian optimization, but generally lots of GPUs is the way to go. It seems works. It's kind of hard to beat, even if you use smarter strategies, a brute force approach. I think that one of my students told me that in his class, he had a student who was doing an internship at Google. At the time, had access to Google Compute. And somehow, on every single homework, this student would produce the best results. Right? So which tells you something about if you do the right hyperparameter search, you can obviously find the best architecture, the best results, and so forth. Right? So which is, there's a lots of papers, lots of work where people are trying to figure out, can you actually design algorithms that can automatically find the right architecture, find the right structure, and such. And this is an open area of research. Let me show you what these hyperparameters are. This was the original model by Alex Krzyzewski, which people called AlexNet. You have an input, you have five convolutional layers, then you have a fully connected layer, and then you have an output. This was the original model in 2012. In this case, people looked at how many layers you have. 1, 2, 3, 4, 5, 6, 7. So you have 7 layers, and people said, whoa, that's a lot of layers. It's a lot of compute that you need to do. And so they were achieving about 18% top 5 error. So top 5 error basically means that you make 5 predictions, you take the top 5 classes, and if the correct class is among the top 5, you're considering to be correct prediction, right? This is just to avoid any noise like the one that I've shown you. So if you remove the fully connected layer, you basically drop the 16 million parameters, and you only have 1.1% drop in performance. It's not that much. So you've reduced the number of parameters by a lot, and you're not losing the accuracy, which was interesting. If you drop layers 3, 4, 5, and 7, and just train this model, then you basically have 50 million reduction in parameters, but you have like a 34% drop in performance, which is significant. Your model basically sucks. And so the idea here was the depth of the network is important. So people started realizing that the depth is important. So what can we do here? And then in 2014, Google released this GoogleNet paper, which had 24 layers. Right? So they went from 9 to 24. And you can see that this was the winning, model at that time in 2014. So they've improved substantially as an accuracy, classification accuracy. One interesting thing about this model is that they've introduced these additional loss functions. So this would be softmax output, right? And this would be softmax output. This would be softmax output. So basically the idea here is that if you sticking the label here, the gradients can propagate through. And these gradients can propagate through. And these gradients can propagate through. The reason why, if you just look at the very top, it was difficult, at least for this model, to propagate gradients all the way through the network. And this is something that we've discussed before, right? This idea that if you have a lot of different layers, it takes a long time for the gradients to go through the network, right? Because of non-linearity. So they found by adding these auxiliary predictions, it was actually helping them. It's interesting. At about the same time, I should point out there was another model that I'm not showing here, which was also kind of on par with this model. Performance was about the same, that came out of Oxford. It's called VGGNet. And the VGGNet basically said, forget about any sort of complex architectures. What we're going to do is we're going to run convolutions. So these are images. So in ImageNet, the images are about 250 by 250 or 225 by 225. These are pretty big images, right? So that what VGG network did, and folks from Oxford, is that they basically applied 3x3 convolutions. So 3x3 convolutions, then 3x3 convolutions, then 3x3 convolutions. I think they had like 16 layers of 3x3 convolutions. And that model was giving the same performance as this one, which is really remarkable. If you think about looking at 250 by 250 image, what can 3x3 convolutions do? It's like you're looking at 3 pixels by 3 pixels, and you're looking, is there a feature here? Right? And you're scanning the whole image. At the next layer, again, you're looking at 3x3 convolution and such. So again, that tells you something about the architecture and what you do is very important, right? And no one knows precisely exactly what is the right architecture to use. Google also was using something that's called InceptionNet, which is using multiple filter scales at each layer. So the idea basically, ooh, something is wrong here. I think my PowerPoint is actually doing something funny here. Anyways, you should have slides, the correct slides. But the idea here is that at every single layer, instead of just using 3x3 or 4x4, 5x5 convolution, they were combining multiple filters at the same layer, right? So they would have a 3x3, and they have 1x1, and they have 5x5. So they were looking at multiple scales for every single layer. And that seems to help model performance. Yes? It's exactly what it is. It's like just scaling of each pixel. That's all. And you'd be surprised. You look at this and say, like, why is this helping? It helps a lot, actually. Yes?
Loss against in the intermediate layers?
So for the intermediate layer, it's the same target. You're still trying to predict that there is a cat here, it's a cat here, and it's a cat here.
So wouldn't the right side become more like an encoder-decoder structure? The predictions are the same in the intermediate layers?
Yeah, so the idea here is that they're not really trying to augment with any auxiliary task. There is no encoder-decoder here. They're just basically saying, I want the output of this to correctly predict the class. And I want the output of this to correctly predict the class. And I want the output of this to correctly predict the class. So you have you're adding 3 loss functions, and each one of them is trying to predict the correct class. This was done primarily for the gradient propagation, right? So that the gradients from here can impact this thing. So that seemed to help when they were implementing it. At least that was the architecture. Yes?
So in this architecture, do all of them, all the heads achieve roughly the same accuracy?
I don't know. I think that ultimately they just optimized for this one. So when you're actually running the model for testing, you just look at this prediction. And the way to think about this may be, I don't know whether they've done it, but you can weight the loss here more, a little heavier than these ones, right? Because it's a linear combination of all the losses. You can just add them up and such. So there are some details in this architecture that you should look at the paper, how they've done it. But that was roughly what the proposal was. Yeah. Yeah, you want to have shallower models. For what? For sure, but then you want to have high accuracy, right? So there's always a trade-off between computation and accuracy, for sure. Yes? Probably. I mean, you are reducing, that's true. I don't know. Yeah. It's an interesting, because like if you look at VGGNet, these are 3x3 convolutions. And no one, like if I look at 250 by 250 image, my initial pry would be to use like 10 by 10 convolution because I can see an edge, or to use 15 by 15 convolution because I can see some structure that I'm picking. What can you do with 3 by 3 convolution? It's just like some combination of pixels. But it turns out to be very important. I think in many cases, if you think about the whole architecture here, is that the number of parameters here is actually not that much. It's only on the order of 1 million parameters, right? So what people just discovered is that there's somehow, you want to include more parameters in the model because you have a large data set, so you want to inject more parameters so that the model can learn it, at least fit the data set. One way of doing it would be to increase the depth or to increase the width, right? So that's what's been happening in that. Sure.
Is there any high-level theoretical explanation of why adding this to data is?
No, I think that the question is like, is there in particular a theoretical explanation as to why you need more or why you need not really?
Why depth is good or
No.
why it should be out?
I think there is some work in computational theory, in sort of complexity, where you can design certain circuits and you can show that there is an exponential gain for some, if you have more depth compared to flat, compared to a flat. But these are very if you look at Boolean circuits and if you look at, more on computer theory side, there is some justification, I think, but not quite anything that connects to these models so far. So we don't really know. And then basically, one thing that they've done is they removed the fully connected layers on top completely. So the number of parameters is reduced to 5 million. So our original model had 60 million parameters. This model has 5 million parameters, even though it's deeper. And it was achieving 6.7 top 5 validation error on ImageNet, which actually was really good. And then in 2016, there was a paper called Residual Network, which is the current state of the art. So the residual network, if you look at the overall model here, I think that the model has 154 layers, something crazy like that. So it's even way deeper. But the idea that these folks have is actually a pretty interesting one. So really deep convnets don't train well. So here's an example of a CIFAR10 data set. And I think that this is the training error when you're training a 20-layer model. And this is the training error when you train a 56-layer model, right? And this is the test error. So something interesting to observe here. The 50-layer model is more expressive, right? It has more parameters. It should fit the data better, right? But it doesn't. So that clearly shows optimization problem. You just can't optimize it, right? Because you have more parameters, you have more expressive model, it should fit the data better on the training. We're not talking about generalization, just the training, right? So it's very hard to train these deep networks. And so what they've done is they've introduced these sort of called residual connections. So they basically say, here's an X. What I'm going to do is I'm going to have this skip connection, which is just the identity. And now I'm going to have these two nonlinearities, and my output here is just going to be the combination of both. This is nonlinear part, this is linear part. Okay? And that turns out to be quite an important thing, because what happens if you compute the gradients can flow through nonlinearities, but the gradients can also flow through identity, right? And when they flow through identity, it's just like you know, just propagating them without any bottlenecks. So skip connection's been around for quite some time. It's just that the residual network really made it work on these challenging tasks. And with ensembles, with ensembling, you're basically achieving like 3.5 top 5 test error on ImageNet, which is on par with human level performance. Like, it's very hard to go beyond that. So this was out of Microsoft on that particular data set, which is pretty interesting. So now these types of models, residual networks, combined with InceptionNet type of models, are the current state of the art. And it's kind of interesting. There was a big race in 2015, 2016 between all the big IT companies. It's like Microsoft would say, whoa, we're reaching 4.5% error. And then Google said, we're reaching 4.35% error. And then Baidu said, we're reaching 3.2% 5% error, right? So everybody was trying to figure out what the right architectures are. And then ultimately, this is coming out of Microsoft research that basically pulled up this particular model, which is the current state of the art. So in many cases, if you look at papers, anytime you're processing visual input, chances are you're going to be using residual networks. Just because the feature that you're getting, and then it's interesting that if I use residual networks and I take the top level features and I apply them to some task, like detection task or classification task or whatever the task you might want to do, generally speaking, what's been happening is that the better your error on ImageNet, the better the performance of those features would be on a downstream task. So there is a very clear transfer for a lot of different tasks using sort of these features. So it's kind of funny because 5-6 years ago, everybody was using SIFT. If some of you remember, like the first thing you do, you compute SIFT, that's your features, and then you do your machine learning. Now you run ResNet, you take your features, and then you do your vision and machine learning, right? So obviously, the nice thing about these models is that in principle, you can backpropagate to them. So you can fine tune your features, your ResNet features. Couple of things in terms of choosing the architectures. Obviously, it's task dependent, right? For different tasks, you might need different architectures. Typically, people do hyperparameter search using cross-validation. And in many cases, the standard approach is you do convolution. Sometimes you do pooling. You might end up going through fully connected layers, so might not actually. Now, with InceptionNet, you don't even need the fully connected layer. Just average the top features. And obviously, the idea is that the more data you have, the more layers, the more kernels, and such. So everybody, that's why it's interesting for these models, is that the more data you have, the better the performance of these models. So if you look at the IT sector, there's a lot of resources dedicated to how do you make these things scalable, how do you get even bigger data set, and such, right? Because with these models, there is a joke that basically says, how do you do computer vision or deep learning on the task? And then task 1, collect data. Task 2, collect more data. And then task 3, go to task 1, right? Pretty much. So that's what's kind of is happening with these models. But the remarkable thing is that they work surprisingly well. You'll be amazed how well these systems are working given enough data. It's a bottleneck, but they work remarkably well. So some of the optimization tricks. Stochastic gradient descent with momentum, batch normalization, and dropout usually works really well, right? That's basically the current state of the art, right? Obviously, you have to tune things like the dropout rates, the learning rates, and so forth, but basically, you need 3 pieces to make it work. And then here's sort of a hand design rule of picking up the learning rate. There are algorithms, you can look at the slides, I think you look at the deep learning book, where you can adaptively choose the learning rate. There's something called ADAM, ADAGRAD, RMSProp, like various versions of picking up the learning rate. But at the same time, a good rule of thumb is that you start with a large learning rate and you divide it by 2 until the loss doesn't diverge. And then you're basically decaying learning rate by a factor of 100 by the end of learning, right? So for example, if you look at this paper, what's happening here is that you're reducing your learning rate by a factor of 2, right? And you have this big drop. And then by a factor of 2, you have this another drop. So if you actually look at the training curves, it's like you're training it and then somebody manually divides the learning rate by 2, you have, and such. So it's very difficult to pick the optimal learning rate. So when you're writing your paper, you could say, I start with a learning rate of 0.1, I train for 100 epochs, I go drink some coffee, I come back, I decrease my learning rate by 2, I go drink some more coffee, divide it by 2, drink some more coffee, now this is my result, right? And it's very hard to beat that particular procedure. So there's still lots of room for improvement Sorry, just a second. So typically, ReLU is the most commonly used nonlinearity. You also want to initialize parameters so that each feature across layers has similar variance, right? So to avoid unison saturation. So there are a whole bunch of initialization techniques you should look and should think about. Couple of things about visualization. So you want to check the gradients numerically, for example, by using finite differences methods. You either use PyTorch and TensorFlow, or if you're designing your own gradient-based algorithm, you might want to do it by finite differences. One of the things you want to do is you typically want to visualize the features. So here's an example of a good training of hidden activations, right? If you look at the samples, and these are your hidden units, you can see that the hidden units are sparse across samples, and they're uncorrelated, okay? Because in many cases, when you're training the model, you typically don't know, is it training? How good is it? Does it do something reasonable? If it gets stuck at a certain position, what's going on? If you look at the activations of your hidden units, they should have this particular structure, right? Let me just quickly jump to this particular example. This is an example of something is wrong with your training procedure, right? Because let's look at this example. This hidden unit is basically off for all the samples, right? That basically tells you that this is a dead unit. It doesn't really carry any information, right? If your unit is 0 all the time, it's a useless feature, right? I hope you can see that. Or if the unit is, if you're using, for example, sigmoid, if your unit is 1 all the time, it also doesn't carry any information, right? You also have units that are highly correlated. Like if you look at this unit, it's the same as pretty much as this one. So you have both units doing the same thing, which is bad, right? Yeah, there's no skip connections, but this is just, again, whether there are skip connections or no skip connection doesn't really matter. You're looking at the activations of hidden units, right? You want to make sure that you don't see these kinds of patterns. Here's an example of visualizing the first layer filters, right? In many cases, if your filter size is like 5 by 5 or 7 by 7, this is at least for images, this is what the filters should look like. A lot of them would look like edges and sort of at different orientations and such. And this is kind of interesting because there is a belief that there is a very nice connection to neuroscience here. Apparently, the V1 of visual area of the human cortex, visual cortex, the assumption is that we kind of like have something similar. Like as a human, when you look at something, your first processing of edges where things are. Because that's the contrast, immediate contrast for you to recognize what the thing, what is it that you're looking at. And these are the examples of bad training, right? Like this doesn't really say anything. This is bad because it's just like the same features are repeated basically. Or something like that, there is a lack of structure. What is it trying to extract? I have no idea. At least in the visual domain. If you go into some other domain, I don't know, like processing some other images, not images of natural scenes, but some other images, then it becomes more difficult to figure out what this should look like, obviously, right? And this example of bad training. Okay, so I think that's the last slide on my side. Couple of words, and we should be done. So next class, we're going to look at the deep Q networks. We're going to be combining these models with Q-learning. And if any of you are planning to work on projects where you're going to be processing images, high-dimensional images, either coming from virtual environments or from real world, you're pretty much going to end up using some form of a convolutional neural network. Okay? You have the reading material to do. There's a deep learning book. It's free. It's an excellent resource to look at these models and see how they work. Obviously, for packages, you have TensorFlow, PyTorch, and Keras, and all the kind of packages that basically do it for you. So, all right.